Welcome to day 17 in Unit 7. Number 9 was a bonus, remember, so hopefully you have already uploaded that if you were going to in the bonus link. First one, we want a 4th degree Maclaurin for e to the x, so that's all positives, every power, every factorial, so we have that written there. Well, we want to approximate e, which is e to the first, so sub in 1 for all of your x's, and we get 65/24. We want to estimate the error with Lagrange error bound. Well, Maclaurin, we're centered at 0. We're approximating with 1, so we need to think on 0 to 1, what's a nice maximum y value? Well, 0 to 1, e to the x is increasing, so e to the first would be the largest there. That's like 2.7 and change, so something that's nice that's bigger than that is 3. So then we have 1, which is what we were approximating, minus our center, raised to the next power over the next factorial. We get 1/40. 5th degree Maclaurin for natural log of 1 plus x. We've seen before natural log of 1 minus x. It's all negatives. No factorials. You're just minus x to the first over 1 minus x squared over 2 and so on. Well, natural log of 1 plus x is that with a negative x subbed in, so now we get the alternating signs. Cut that off at the 5th degree, because that's what they asked for. Notice if we have natural log of 1 plus x, that means we want to sub in 0.2 for 1.2. And when you do that, you get that 34,187 fraction there. Our error, we would need to look at the next derivative. So we're going to have to look at our 6th derivative. So here's all the derivatives of that natural log of 1 plus x. Eventually we get down to that 6th derivative. We were working with Maclaurin, so we've got to start at 0 and go to what we were going to be subbing in, so 0.2. For that derivative to be big, we want the denominator to be small, meaning 0 would give us the biggest thing. When you put in 0, we get a negative 120. M is the magnitude, so we always do the absolute value of it, so we'll put 120 in for M. Then we'll have what we subbed in the 0.2 minus our center of 0 and the absolute value, raised to the next power over the next factorial, and we get that 1 over 93,750 number. In 3, we got our 5th degree for e. We just worked with e a second ago. We want to do e squared, so sub in 2 for everything, and we get 109 over 15. We need that because if we're going to put bounds on it, we want to do our approximate, and then we'll do plus or minus whatever our error is. So we need to think the interval of 0 to 2 for our 6th derivative of e. Well, nicely, e's 6th derivative is just itself for e to the x. So that's an increasing function. So at 2 is when it will be its largest value. Well, if e is like 2.7 squared, we can be comfortable knowing that 9 is a nice value larger than that, because that would be 3 squared. So we have 9 in the m spot. Then we have the 2, which is what we are approximating, minus our center, raised to that next power of 6 over the next factorial of 6. Heating that up, you end up getting 4/5. So to put bounds on e squared, we would take our approximation of 109 over 15, subtract the 4/5, and also add the 4/5, and we know e squared has to be in between there. Often you will see it left as this. Okay, just leave it with the plus and minus there. If you combine them, that's perfectly fine too, but more frequently you see that first option. All right, so I wrote out the 3rd degree over on the left and did the approximation, but they didn't want that because they just wanted the error. We know whenever we're working with sine and cos, we can always just let m equal 1. So we have 1, then we have the minus point through that we're subbing in, minus the center of 0 because it's Maclaurin, raised to the next power over the next factorial, so raised to the 4th over 4 factorial, and we get that 27 over 80,000. Secondary Maclaurin for cos. So a couple ways we can do that. Do several derivatives out, doing your chain rule. Sub in 0 to get each of your derivatives. Build it out. Or the shortcut way is just take out what we know for cos and fill in the 2x plus pi over 3. They'll end up being equivalent values. So for the error, we do need to have all our derivatives out. So we need to get to the third derivative, and notice that that coefficient is 8, because that means now our m value has to be 8 for this, as opposed to like when we just have regular sine and cos, it's just a 1. So that next power is 3, the next factorial would be 3 factorial, and because we were doing it at 0.1 for the first one, that's why we have 0.1 minus 0. We get 1 over 750. Only thing that changes in B is we wanted minus 0.2, so you have the minus 0.2 minus 0. So second degree for sine centered at pi over 3. To estimate our error, we know that our m we always use for a plain old sine or cos is 1. We're doing sine of 1, so we'll have 1 minus our center, so 1 minus pi over 3 raised to our next power of 3 over our next factorial of 3 factorial. When we do that, we get that 0.0000175 number. Now, if we want that to be within 10 to the negative 9, whenever you're finding what term for a sine or cos, have in your head ahead of time evens or odds. So we know sine, our answer here has to be an odd. If you get an even answer, you know that's wrong. So we have 1, because we were working with a sine here. The 1 minus pi over 3 raised to the next power over the next factorial. Put that in a graphs page and scroll down. And we only care really about the odds. So 1 is not small enough. 3 was not small enough because we would need 8 zeros if it's 10 to the negative 9. 5 would be small enough. Now, because we put it in as n plus 1, whatever one we have is just our answer. If you had put it in as raised to the n and over n factorial, then whatever you have is your error, and then you'd have to go to the previous term. We'll see in upcoming days that sometimes that putting it as n might be easier to think about. But for now, I have this one written here as the n plus 1. Next one is pretty similar idea. This time, though, we are centered at 0 because it was Maclaurin, and we were subbing in 3. But other than that, m is the same. You got the n plus 1 over n plus 1 factorial. Remember to only look at the odds. 11 was not small enough. 13 was. And because we put it in as n plus 1s, that's what we want, the 13th. Now in 8, we're doing cos. You need to think right from the start, okay, my answer needs to be an even degree. So we did cos of 1, so you had 1 minus 0. M was 1, raised to the n plus 1 over n plus 1 factorial. So 4, nope. 6, not enough. I didn't even show it in the table here, but 7 was enough, but 8 is the one that we would want because we're only looking at the evens. So make sure, if you're working with sine or cos, you're only picking out a degree that matches the type of powers that we have. So 8th degree would be our answer. All right, because we're going to be in day 17 notes in your notes packet. We're going to do another day of practice with Lagrange error bound. Our fourth example that we see today, it will be a really important one because that's how Lagrange shows up on the AP exam. So first one, we're going to use a third degree Taylor centered at 1 to approximate natural log of 1.5. So we're going to start with f of x as natural log of x. So the derivative is 1 over x. That's really x to the negative 1. So its derivative would be negative 1 x to the negative 2, or in other words, negative 1 over x squared. Its derivative would be 2x to the negative 3, or in other words, that's 2 over x cubed. If we sub in 1, natural log of 1 is 0. 1 over 1 is 1. Negative 1 over 1 squared is negative 1. 2 over 1 cubed is 2. So we're going to have 0 over 0 factorial plus 1 over 1 factorial. We're centered at x equals 1, so we'll have x minus 1 to the first. minus 1 over 2 factorial times x minus 1 to the second equals 2 over 3 factorial times x minus 1 to the third. And we could leave it right like that, or if we wanted to neaten it up, 0 over 0 factorial is 0 over 1, so that's gone. The next term we would just have is x minus 1. 1 over 2 factorial, so that'd be minus 1 half, x minus 1 squared. And then we would have plus 2 over 3 factorial is 2 6, so we'd have 1/3 x minus 1 cubed. So to approximate at 1.5, just stub in 1.5 for each of those. It's really like we'll have 0.5s. And we'll end up getting, when we do that, 5/12, or if you did it to 3 decimal places, 0.416, and the 6 would be repeating. Well, now in part B, we want to know, okay, well, what's our error for that? How close is that really? So we're going to use Lagrange error bound. We know because we put in 1.5, we'll have 1.5 minus our center of 1. We know we've got to have the next power and the next factorial. So we'll really have 4 and then 4 factorial. Well, to find m, we first need to know what our fourth derivative is. Well, if we go back here, here's our third derivative, so the fourth derivative will be negative 6x to the negative 4. Or written in a nicer way, that's negative 6 over x to the fourth. So we've got to consider that we have the interval 1 to 1.5. We want to think, what's an upper bound on that interval of that fourth derivative? Well, to be a big value, our fraction denominator wants to be small. So we would want to put the smaller number in there, the 1. When we sub in 1, negative 6 over 1 to the fourth is negative 6. But for m, we always use the magnitude, or in other words, the absolute value of it, so we would want to use 6. So that's kind of the thought process you go through. You get your next derivative, and then think about on your interval what's going to yield the largest value. If it's something nice, when you sub it in, just use that. If it's something not nice, pick a nice number a little bit above that. So therefore, to find our remainder, we would do our m value times the absolute value of 1.5 minus 1, absolute value to the fourth, and then this would be over 4 factorial. If we punch that in and neaten it up, we would just get 1/64. So that third degree approximation, we know by Lagrange error bound, is within 1/64 of the value, the exact value of natural log of 1.5. All right, so our next one, we're working with cos. We want to find what degree we would need to be within 0.0001 of the actual value of cos of a fourth. Right at the start, I'm already telling myself, okay, I know my answer's got to be an even degree, because cos is only even powers when we do its Taylor polynomial. So we know that no matter what derivative we work with, it's either going to be plus or minus some cos, or it's going to be plus or minus some sine for any derivative value. Therefore, no matter where we are on our interval, a nice max value for sine and cos is always going to be 1. So over here, we're going to have 1. We know we got to have 1/4 minus 0, because it's the value we subbed in minus the center. And then we don't know what our next power and next factorial are going to be. That's what we want to figure out. So we would put this in our calculator in a graphs page, but for x. So if we go over to a calculator page, or a graphs page, sorry. We're going to have 1. We'll have our absolute value. Now, in reality, because we know 1/4 minus 0 is a positive, you don't have to do the absolute value. So I have 0.25 raised to the x plus 1. Now down in the bottom, make sure you put the x plus 1 in parentheses and then your factorial. So we'll do our control T, and we're looking to be less than or equal to 0.0001. Well, that's the same as 1 times 10 to the negative 4. And we're only going to really care about the even powers. So 2 was not small enough, 0.0002. 4 was our first even power that is small enough. Okay, so you kind of just pass over the odds, and we're only looking at the evens because it was cos. So just so fill it in here, we had like 0.031, we had 0.0026, that's still too big. Now at 3 we get 0.00016, which was still too big, but even if it was small, we wouldn't care about it because it's an odd. So then we had 5 zeros, 8, 1, 3. So fourth is the one that we want. So we would need a fourth degree polynomial. Now just to check it, just to show you that it works, cos of a fourth, if we put it in, is 0.9689 and some other stuff. So if we did, say, a second degree Taylor for cos, that would be 1 minus x squared over 2 factorial. So if you did your second degree polynomial at 1/4, you would have found that it was 0.96875. So too far off from where we want. It's not within 0.0001. But then if you did the fourth degree, which would be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, if you did that at 1/4, you would find it is 0.9689127, which is going to be within that 0.0001. So you wouldn't need to do this check part normally, but that's just to kind of show you that it does work. All right, this last question we're going to look at in this video is a really important one because it's how Lagrange error shows up on the AP exam. When we've been doing problems where you get to pick the M, it's kind of subjective. There could be cases where you might pick a different nice value of M that's a upper bound than like your neighbor. So the AP wants to make sure that everyone picks the same value of M, so everyone's getting the same answer. So first off, they'll usually ask you to approximate something. So we're going to approximate f of 2.5. And what you do is you write a polynomial to the best of the ability based on the information. They give us up to the second derivative. We don't have the value of the, or sorry, up to the first derivative. We don't have a value of the second derivative, we just know about its upper bound. So the best we can do is write a first degree polynomial. So we would have 8 plus 5 over 1 factorial times x minus 2. And we know it's got to be x minus 2 because our derivatives are happening at 2. Well, now what we do is we just sub in 2.5 for our approximation. So 8 plus 5 times 2.5 minus 2. Well, that's really a half times 5, which is 2.5, plus our 8, which would give us 10.5. So now we need to fill in to find what our remainder is. Well, our m value should be the upper bound of our next derivative. Well, that's where this comes in. They tell us that our second derivative is always going to be less than or equal to 3. So that would then lead everyone to have a 3 in your m spot. And you're going to see 3 on the homework that are like this. I believe it's the last 3 questions where you'll have to work with this. Well, now we'll just do our 2.5 minus our center of 2. Our next factor or next power is 2, and that next factorial is 2. And if we sub this in, we just end up getting 3/8. Now, one thing you'll see on the homework is it might ask you to prove something that like that that f of 2.5 is within something. Well, if you need to do that, you just use your error. Like in this case, we would know that f of 2.5 is either 10 is within 10.5 minus 3/8 and 10.5 plus 3/8. So maybe it would say for r's, prove that f of 2.5 is 10 point something. Well, if you subtract the 3.8 and add the 3.8, that's definitely 10 point something, so then we would have proved that. The one on the two on the homework, one will ask you to prove it's negative, the other will ask you to prove that it's not some value. Like for example, this would prove that f of 2.5 can't possibly be 9, because 9 would not be in the interval here. That's it for this video. Have a great rest of your day.